Hey guys, it's time for another Black Ops talk. For those who haven't been here before, actually, who here is actually your first time at one of my talks? Cool. Is it just me or is Black Hat a little bigger this year? Wait, I guess you guys wouldn't know. But trust me, it's a lot bigger. I'm seeing a lot of new faces here. I'm seeing a lot of energy. Cool. So what's up? What are we up to? This is going to be my 7th talk here at Black Hat. This is actually my grandmother's 4th Black Hat, which means she, I guess, is more elite than you are. I tend to do strange, for those who are new, my history is I tend to do strange things to stranger protocols. I've done a lot of stuff with SSH, I've done massive network scanning, a lot of stuff with DNS, pattern analysis, and neutrality verification. This year I'm thinking, I need a new target. What should I play with? And you know, I've been trying to stay away from the web. I mean, it's just been such a tempting target. But you know, there's just so much to play with. Okay, and don't worry, it's mobile too. The best part was actually not having to Photoshop an iPhone in. It looks close enough. The web is enormous. The browsers, you know, everyone talks about the browser like it's an operating system. No. The real way to think of the browser is that it's this network stack on crack. It's a TCP/IP stack, but don't worry, you get to send it code, you get to give referrals to other protocols. It'll even make pretty pictures for you. This is a network stack to play with. So, there's been a lot of stuff that I've been hearing about the web. You know, we've had a lot of stuff with cross-site scripting, with cross-site request forgery going on, where the security model of the web, remember, the original security model of the web is anyone can go anywhere, things can be pulled in from all over the place, and this worked great until about the moment there was private content hosted on websites. Then not with the so much. We had an attack on the Super Bowl, where 2 days before the Super Bowl, the attackers actually put a malicious image up. And, you know, we haven't been seeing million-plus worms in some time. They got million-plus desktops compromised overnight. But what really got my attention was actually this DNS rebinding test done by Dan Benet's team over at Stanford. DNS rebinding is something I'll explain in a bit, but they basically put this Flash applet on an ad network. Advertising networks allow you to take an individual banner ad and distribute it across lots and lots of different pages. This applet acquired network connectivity, because of a DNS trick, to over 100,000 client networks. Okay, DNS, tunneling, behind firewalls, I gotta get in on that. And I've been trying to avoid DNS, but no, I need to take a look at this. Turns out, this is an old bug. This issue dates back to actually 1996. It's one of the few things that has actually, like, come back from the dead. Everyone forgot about it, and all the new code forgot to keep working on it. A lot of the research and mitigation has been being driven by Dan Benet's group over at Stanford. What is the effect of this attack? And I'll explain it in a bit. It really breaks the security policy of the web. How does it work? How does the web itself work? You have a web browser, and it pulls resources in from all over the place. An image comes from here, a music file comes from there, you get some HTML, maybe you'll grab some script over from Google. In fact, you can even go so far as to have a little box on your web page that is some completely different web page over on some completely different site. We call this an iframe, internal frame. Now, this is part of the design of the web. But what if someone embedded Hotmail inside of their own site? What if you were logged into Hotmail? Would this person be able to look inside the iframe and see exactly what's going on, read all your mail? Well, this would clearly be a problem. Even back when they were looking at spreading the web, they realized it'd be a problem if your private stuff could be embedded in other people's public pages, and then the public pages could look inside. So what got created was something called the same origin policy, which can be thought of as look, but don't touch. A web page can embed it, you can use it, everything is great and wonderful from the user's perspective, but from the page designer's perspective, they can't peek inside because it's not their content to look at. Now, if they know how to get it themselves, they can go ahead and they can run a web browser and they can know your password, but they're not going to get it just because your machine happens to have a cookie that'll get you in. So the basic idea is, if foo.com has an iframe to foo.com, yeah, you can look inside. You're the same site. But if foo.com has an iframe to bar, no, that's not going to work. The security policy is if two things come from the same place, they must be trusted the same. Seems reasonable, right? No. Problem is that the trust is associated with names. Content doesn't come from names. When someone calls you on the phone, it's not a name that is calling you. It's a phone number that is calling you. Everything comes from IP addresses. Now, we happen to use this technology called DNS to translate between a name and an IP address. So you might look up foo.com and get 1.2.3.4. You might look up bar.com and get 3.4.5.6. And then you make a connection to the addresses at each of those IPs. The assumption is that those translations are mostly static, they stay the same, and no one would ever return someone else's IP address. That's a great assumption until up to the point there's a bad guy involved. Bad guys return whatever the heck they feel like. So, now my screen goes blank. So hang on a second. Alright, so now what is the actual crux of the attack? One moment, bar.com. Very nice site, you got a bar.com, you like going to bars? Points to a server over in Europe. The next moment, that same name goes to a printer down the hall. Now suppose your browser loaded a page from each address. Well, the content from the European server would be at bar.com. The content from the printer down the hall would be at bar.com. Now you have two pages, same name, totally different place they came from. But the browser doesn't know. It has no way of knowing. And so what happens is that the server in Europe, it may not be able to talk directly to the printer because, it's in Europe, it's not down the hall, but it can talk to you, and you can talk to the printer. So it just bounces off you. So all this stuff is by design. If you actually made it a pain to try to fix, because the fact that resources can actually be hosted all over the place, all around the world, is actually key to the global reach of the web. You have a website that you want everyone in the world to reach, you're going to put servers all over the place. And so you actually have a direct need for servers in totally different locations to be able to script against each other's resources. It just so happens that allows the server over in Europe to script against the printer down the hall. So, the canonical attack, and there are more, is the firewall bypass, based on the fact that most corporate networks draw a significant distinction between the external network and the internal network. And the idea is that you have a lured browser and you're going to hijack them. You're going to take the browser, and even though you can't reach stuff, it can. And you can drive it around. So what are our levels of exploitation here? I completely encourage you to go back and check out the original research on this from Benet and from a couple others. Arsnake's been doing a lot of work on this too. But I'll give you the introduction. The first level of exploitation is where you use just the browser and nothing else. It turns out, what I was talking about with iframes, where you have little copies of the web page, works great. You have an iframe, you look inside, you see what's in there. Perfect. This gives you arbitrary HTTP resources. The next level is actually the web plugins. Say MSXML, the XML HTTP requests, Silverlight. These web plugins actually have support for a bit more flexibility in their programming interface when you retrieve content. So it's basically enough not just to talk to websites, but to talk to web services and to talk to, provide semi-arbitrary headers. There's a little bit of control in terms of what headers you can put onto an XML HTTP request, but it's certainly more flexible than you have with iframe. The third level, and the thing that really caught my eye, are those things that give you access to sockets. Now, I certainly noticed for all the love of web services, everyone's real excited about being able to access real TCP. And this is actually interesting. If you look at the way the web is being used, The web is built on top of TCP, which is a nice streaming layer. It's reliable. You get to send a byte. You get to receive a byte. It's very, very nice. HTTP is not like that. You get these big messages, and you have URLs. The entire web is desperately trying to crawl its way back to the underlying layer that's byte-oriented. It's kind of funny to watch. At this point, HTTP is TCP with inline headers. So when it comes to the web, when it comes to these level 3 socket plugins, what these are doing is these are giving real sockets to web browsers. These are giving them the holy grail of you don't even need to pretend there's an HTTP layer at all. You just get to send arbitrary bytes directly. Now what this means is the web is starting to get connectivity to things that are very much not the web. Now the web having all sorts of awesome and amazing programmability, this is, what's the term, fantastic. So Java gives us some of this arbitrary TCP and UDP goodness. They have a very nice advantage. They got this problem like 11 years ago and actually dealt with it surprisingly well all the way back then. In their standard interface where you have an applet, it actually looks to see where it downloaded the applet from, where it downloaded the code, and it says, great, this is where my code is from, this one location. I am not setting up a network connection anywhere else. Whatever happens to be said, whatever DNS says, if I got this command from anyone but that guy over there, I'm not connecting to it. Very nice. Totally works. Unfortunately, there's a second way to use Java applets or Java methods. And that's something called Live Connect. And Live Connect allows JavaScript to call the socket interfaces directly without going through the applet interface. You see this in security every once in a while. Very nice, very elegant security system built at exactly the right place. But don't worry, someone else shoved in a shim that goes all the way around. It only works in Firefox and Safari, though. The effect is arbitrary, is high port UDP and some TCP as well. Flash. Flash has worked really, really hard to do this right. I feel bad about having to go into depth about how to actually attack it. They've worked their butt off to actually make a security model that is, frankly, the next generation of probably what the web should be doing. They have all sorts of things involving policy files that they retrieve. All their stuff would work perfectly if it wasn't for those meddling DNS rebindings. The effect you get from Flash is actually arbitrary TCP. They try to limit it to ports above 1024, but that doesn't work. I'll tell you how later. So what are the mechanisms for rebinding an address? Now, there are lots of ways of using it, but how do you actually do this? DNS is really actually built to have names stay static for long periods of time. They're not supposed to flip all the time. For anyone looking at botnets, there's a thing called fast flux, where attackers are swapping their names around all the time. That's an unusual use of the DNS infrastructure. How do you go ahead and bend DNS to your will in this way? Well, there are three methods. One is temporal, one is spatial, one is completely and utterly ridiculous. The first way, the way everyone is knowing to do this, is, there's a timeout on DNS records. You get to say, I'm giving you this record, but please only hold it valid for the next n seconds, with n possibly equal to 0. So you just hand out these records and say, don't store it. Next time you need to see if it's good, come back again. Don't hold this at all. And this actually works quite well on most, but not all networks. There are indeed some networks that establish a minimum time to live. And what that means is, you may say, please only store me for 0 seconds, but it actually stores it for 5 minutes. And these networks are all happy. They're like, oh, we're safe, because you can't rebind us, because we're going to hold on to this address for 5 whole minutes. Because an attacker can't wait 5 whole minutes for their attack to succeed. They're really impatient that way. Yeah, about that. There is another method, and it's called spatial rebind or spatial modulation. When you look up a name, the name can return multiple addresses at the same time. And those records can have like an infinite TTL. Now the question is, which record is the browser actually going to use? I don't know. It'll use one of them. Okay, well, what if it picks the wrong one? Try again. It turns out you can detect in every context when you made a connection to the wrong IP address. So, if you're using spatial modulation, try, and if you don't get the expected results, fail, kill the flash applet, start a new one. Eventually you'll get it right. This was actually a lot of fun when I was testing this, because I just basically, it was a total brute force solution. I'm not getting windows that are necessarily reliably opening up to the right address. I know, I'll open 10. One of them will. And totally did. And this is actually the technical description of how to do it. I have so much to go over. You can refer to the slides, which are not on your CDs or in your books. They'll be on the website. Then there's the fun one. This comes from actually knowing how DNS works. People are trying to use DNS TTLs as a security technology. Guys, they're not a security technology. In fact, finally, we have something even less a security technology than virtual machines. If you'll excuse the annoyance, Tommy the Tank Engine security is not good. I think it's safe, I think it's safe, no. TTE. It turns out that overwriting a TTL, if you actually control the legitimate record, is very, very easy. In fact, it's supposed to be easy. It's by design. When something wasn't designed to be a security technology, please don't be surprised when it doesn't actually act as one. So here's what you do. I call it CNIPing, right? It turns out in DNS, when you look up a name, you can get an address back, or you can get something back called a CNAME record. A CNAME record is, I know you talked to me, but who you really meant to talk to was this name over here. And here's its real address. When you get a referral to a different name, that name can contain, and actually is supposed to contain, the genuine address of that alternate name. That genuine address that comes in the CNAME overrides whatever's in the TTL. It doesn't matter if that thing could have lasted for a year. It's like, okay, well, I got a new name. Got it over there. Came in, it's fresher, it's newer, it's updated. So, to actually look at this in action, we're going to look up 1.foo.mallory.com. 1.foo.mallory.com has been CNAMEd over to bar, and bar has an address of 10.0.0.0. And we look it up, and when you look up bar, it's 10.0.0.0. Now we're going to look up 2.foo.mallory.com. And 2.foo.mallory.com, same CNAME, but now it's going to 10.0.0.1. Take a look. What's the address for bar.foo.mallory.com? 10.0.0.1. Doesn't matter that the TTL didn't expire, guys. The CNAME overrode it. So, to review, by swapping addresses out from underneath the web browser, we can get arbitrary TCP and sometimes UDP access to hosts reachable by the client. Now, what can we do with this? Well, I've been doing tunneling for a long time. Can we VPN completely into corporate networks using nothing but a compromised web browser? Excuse me, a lured web browser. No code execution required. Sure, totally easy. Okay, I'm kidding. It's a bit of a pain in the ass. It took 7 programming languages and 6 protocols, but totally easy. I'm serious. What is up with web programming? Every time you cough, you're in a different language. It's not like a new language. It's like a variant. It's like a smooth continuum of programming. So, how are we going to do it? Well, we have 3 actors in our little dance. We got a browser that has access to the nice and gooey internal resources. We got an attacker that really wants that access. And we got a proxy that wants to bridge the attacker and the attacker and the browser together. So we're going to start with the proxy running software that I wrote. This software is called Slurpee. And I'll explain why in a bit. Slurpee, the proxy, is a multi-protocol server. It's built using the Perl PO environment, the Perl object environment. Very, very nice for actually building systems like this. It speaks a couple protocols. One protocol it speaks it accepts TCP streams for a browser to deliver. Each of those TCP streams has to contain some routing data. So, attacker has streams, got to get serviced over at the browser. Slurpee's going to accept that. Slurpee's also going to accept HTTP requests. Browser's coming in, wants its wants its routable traffic. Slurpee is going to provide that over HTTP. Slurpee also provides DNS support. At the web layer, it needs to route. There's all these routing directions that I'm giving it. How are these routing messages actually transmitted? We're using DNS as a routing protocol, which actually, if you think about it, is totally not even an abuse. And actually, finally, XML socket requests. Flash has a thing called XML socket for determining the policy. What ports are allowed to be connected from what servers. It turns out it's a very simple protocol, but by adding support, we get ports lower than 1024. The basic theme, and I'm going to be reiterating this a couple times, is attacker connects the proxy, which manages the appropriate resources in the browser to service the attacker's connection. That's what's going to happen, because the proxy gets to send code to the browser. Not arbitrary code, not executable code, but not nothing. A proxy gets to update the browser to speak the necessary flash to service the bytes being sent by the attacker. So, now we get into the fun terminology. Browser connects. Establishes an iframe called a bucket. A bucket is a collection of connection managers. And the bucket actually polls, and yeah, it's inefficient, I can fix that, but the bucket polls for new connections to establish. The attacker goes ahead and actually establishes a connection. Tells Slurpee, hey, Slurpee, I want a connection through 10.0.0.1 on port 80. Well, the browser bucket retrieves the list of connections required, compares it to the previous list, goes, that one's new. I don't have a connection available for that. I'm going to create one. Now, what I'm doing, it's a little bit sneaky. I don't actually have the bucket handle its own connections. I don't have it open its own flash objects. No. It opens up an iframe to a second location, to a location that is specific just for that IP address. The name is dynamically created. Remember, I own the name server. I am the name server. Now, this bucket opens up this second level iframe, and it's going to have flash objects to service that particular series of requests. And this second level iframe is called a socket. It's like a socket, but it sucks. So, you end up with a bucket of sockets. So, let's see how this actually works. And unfortunately, I don't have wired nets. I'm not going to be able to give you the live demo. But, we do? We'll try. Demo of how this works. When there's an actual connections to 10.0.0.1, and you'll see over there in the top right, the destination port is 80. We have a bunch of state. Is the client connected? Yeah, the browser's connected, or in the connecting state, the server's connected. We have some data to browser. These are base 64 encoded records that describe, please send record 0, please send record 1, please send record 2, please send record 3. Now you'll see that there's sequence and acts. Yes, I admit it. I ported TCP to JavaScript. I had to. But this is basically the nature of the messages that are getting exchanged back and forth. So, I was very amused when I realized that this was actually the title. In order to get the actual connectivity from the browser to the various destinations, you gotta mess with Flash. We can't do it in JavaScript alone. But I didn't really feel like getting the Flash programming environment, and there was this great language called HAX. Okay, the language is called HAX. I have to use it. HAX actually compiles not just to Flash, but to JavaScript, and I had it create an object for me. A Flash object that I could say, hey, Flash, go ahead and make this connection. And then I had to say, okay, what do I have to do to make Flash make a connection to an arbitrary port? How many DNS queries does it take to get to the center of a corporate network? 3. Query 1, we got to load the movie. We load the movie, that does a DNS query. Query 2, we got to load a security policy, whole new thing. Of course, we're still hosting the security policy. 2. Before we go ahead and do query 3, we got to tell the DNS server, hey, DNS server, you're going somewhere else next time. The next time someone comes to you with a query, where you want to go is actually 10.0.0.1. And it arms. It's ready. It's ready to go. Query 3 happens. We make our connection request to 10.0.0.1, and that goes straight to 10.0.0.1. 3. Now what? We have a connection. We have Flash having a socket to some location. Is that enough? No. Flash needs to actually be able to migrate this data around. So, here is the life cycle of a connection. First, data is received by Flash. There's actually a event that is fired when the socket receives data. Well, Flash is not actually going to be sending the data. Who I want to send the data is actually all the way back up in, not even any of the sockets in JavaScript, in the bucket. I want the bucket to handle communication for all of the children's sockets that are below it. That way I have one nice object that I'm passing back and forth and doing state synchronization on. So, this is what happens when you wave your hand too much. I'm vulnerable to a hand-waving attack, apparently. All right. Can you hear me? Rock on. We're back for more. All right, so check it out. Here's how we're going to do this. I've got a Flash applet. It's receiving data. I don't want the Flash applet sending the data back to the attacker directly or to the proxy directly. I want it to happen all the way back up in the browser. What's one of the other reasons I don't want the Flash applet doing it? If the Flash applet does it, it might send the data back to the socket destination. No. Flash's job is to send the data to the socket. The browser's job is to send the data to the proxy. But don't worry, there's a bridge between Flash and JavaScript. Haxi makes it very nice. It gives us a remoting layer. What we're going to do is we're going to take the data from Flash. We're going to put it into the second level iframe, the socket. The bucket is going to say, oh, I've got to do an update. It's going to go to each of the sockets. It is going to drain each of the sockets of all the bytes on each socket. And is going to pull it all up. Then it's going to send that out. Server's going to receive it. Server's going to acknowledge reception. I'm not going to assume that it arrived correctly. TCP should be reliable, but remember, HTTP, frickin' weird. The proxy is going to receive the update. It is going to send its stuff out on its sockets, on its own sockets, on the attacker sockets. And you know what? The attacker sockets might have some replies, might have some data coming back. So that is going to come into the attacker, and that is going to show up all the way back over in the JavaScript here on toBrowser, and that's going to be sent to the browser. And then on reception, it is going to, hey, we've got a new update block. Everything in the two browsers is sent to the appropriate socket. The socket send it to Flash. Flash puts it out on the socket. Works like a charm. So, you might be thinking, Dan, wait. You've got a bucket at one domain, and you've got these sockets that are at a completely different domain. How come they're allowed to talk? You told me earlier that if two things aren't from the same domain, they're not allowed to talk. But there's this wonderful little exception in same origin policy. I'll totally use all of this stuff to my advantage. It turns out that if a parent frame and a child frame each are in the same parent frame and a child frame are each in the same subdomain, they can both claim and actually allow access to each other. So what happens is my domain in this case, proxyhost.com, or I guess notmallory.com. Why not Mallory? Because seriously, it's not Mallory. It's not a bad guy. What? Why are you looking at me that way? Not Mallory may have bucket.notmallory.com. And may have 1.2.3.4. Whatever random value .notmallory.com. But if they both claim to be in the security domain not Mallory, they'll get the script against each other. Thank you, same origin policy. And that's it. A little bit of housekeeping for opening and closing sockets and eventually entire sockets. Literally, when the second level iframe is no longer useful, it just disappears. It is removed from the DOM. It's very weird to be in a telnet session and hit enter, and then your web browser just starts losing entire objects. Kind of cool though. Haven't talked about the attacker. I haven't talked to you about how it is that the attacker actually gets to open up connections on the proxy. By any chance, let me do a quick time check here. By any chance, was anyone at my first Black Hat talk? Awesome. That is some old school. All right. So Grandma actually made cookies, and I'm going to give them out to anyone who asks a good question. If you were one of the guys at my first talk, you deserve cookies. It was like 7 years ago. All right. First talk, I talked about this thing using Slurp. Slurp used PPTP over SSH. Slurp was a 1995 era tool that turned shell connections that were text only into PPP connections. PPP, of course, standing for pretty pictures. Grandma, I used Slurp on the machine you bought me. I talked about Slurp in 2001. Slurp was old school when I was at my first Black Hat. I don't even know what it is now. What Slurp actually does is, given a stream of packets, create sockets and send the data in the packets to those sockets. Slurp was a user space NAT implementation. Slurp, the most modern version of Slurp, is actually not on the internet. I searched for it for like an hour. And then I'm like, wait, there's no way I don't have it in my archives. I started looking at old hard drives. And sure enough, there we go. So I'm republishing Slurp. I'm bringing Slurp back from the dead. Hell yeah. Check this out. We've got a PPTP daemon. I am so not restating how PPTP works. It's the most hideous protocol on the face of the planet. And that's saying something. I've seen some pretty bad ones lately. In fact, I think I just wrote one. But what PPTP ends up doing from the client perspective is it takes all the packets that are going on, all the sockets, takes everything that would go out to wherever, shoves it all into a PPP stream and sends it at an individual address. PopTop, the Linux PPT daemon, strips off all of this encapsulation and just yields a PPP session. Well, PopTop can talk to Slurp. So PopTop can say, here Slurp, here's a bunch of packets, please turn them into sockets and go do some good stuff. What if we were to modify Slurp a little, that instead of doing its own sockets, it went to Slurpy? And it said, hey Slurpy, why don't you find a web browser somewhere to go ahead and complete my sockets? That's actually why it's called Slurpy. It bridges Slurp with IE. Oh yeah. So, our final idea here, the attacker runs applications that use sockets. The sockets get sent over a PPT link to Slurp. Slurp provides a set of streams to the proxy. The proxy tells the browser's bucket to open up the appropriate sockets. The proxy tells the browser's bucket to open appropriate sockets. The browser opens the sockets as commanded, sockets as demanded. The sockets provide socket level access. The proxy can now mediate traffic between the attacker's sockets and the browser sockets, and now we get to have fun. We get Nessus over IE, Nessie. We get World of Warcraft over IE, Wowie. We get pretty much anything we want. I'd love to give you the demo, but unfortunately the network conventions are a little bit odd for it. Pull me aside though, I have it all ready. Well, sort of. So what else can we use this for? Doing a quick time check. Oh, you guys have no idea how disturbing this is all going to get. Things other people have mentioned. Click fraud's a real problem. Before we assumed we knew what the browser was doing. We had controls, we had headers the browser was always going to do. Now the browser can make arbitrary TCP sessions, which means the browser can have really arbitrary sockets and can behave in really arbitrary ways. It's very, very hard to detect a suitably compromised browser. The only thing you can do is detect that it's unable to transmit certain cookies. A real browser would know a certain cookie value. A click fraud browser would not. Spam. Yeah, you get port 25 access too, guys. You can start sending, go to a website, you start sending spam. What else is going on? I've been starting to think about what we can use this for. Stealth Tor, you go to a website and you are just sort of included into a global network of connection completers that then just sends the traffic back. We can do some bunch of stuff to protect network neutrality. Peer-to-peer networking, actually, we can do. Java provides UDP support, and Java is giving us the ability to send UDP to arbitrary places. We can create a whole cloud of browsers that are all communicating with one another. Oh, and there's this one thing at a TCP/IP drinking game. IP over spam. Sorry, Grandma, I was a little inebriated. TCP/IP drinking game. And the question I was asked was, how would you get around the Great Firewall of China? Now, the correct answer was, why do set packets that the Great Firewall is sending? Because it's not actually blocking traffic, it's just trying to send shutdown messages. A trick we're going to exploit later. My answer was a rather more disturbing one. I'm like, China sends a lot of spam and China receives a lot of spam, so why don't we just encapsulate our IP traffic inside of that? This was a joke. As then I'm looking at this, I'm like, well, I'm receiving IP traffic and I can send spam. Oh dear God, I can do this with a browser. Are people actually interested in this whole network neutrality thing? I talked a little about tools to detect violations of network neutrality last year. And it was a total accident. I fell backwards into this. I'm like, oh, I can see when the network's getting slower. I had no idea there was so much interest in this. I really didn't. So I've spent the last year thinking, and you'll note this is not in the slide talk. I say nothing. Last year's method had a bug. I needed to send so much traffic that I caused packets to be dropped on the network. I do try not to send so much traffic that I cause links to die. It turns out that really annoys people. So I started thinking, is there a way I can detect? And then I stopped talking about network neutrality. What we're looking for is provider hostility. If you're sniffing my traffic, you're a hostile network. If you're altering my traffic, you're a hostile network. If you're censoring, if you're slowing it down, you're a hostile network. And man, if you are selling my traffic, you're really hostile. Let me give you a metric for hostility. Would the US Army kill you for doing it? You're probably hostile. So what do we need in order to detect provider hostility? Well, if you go ahead and you download content from two different sites at two separate speeds, there's too many complicating factors. One has a better host than the other. There was some traffic on the particular route. There's all these factors that are conflated. The basic thing you need in order to find out that that something is happening because of your local provider, the entire rest of the internet has to act exactly the same. So, given identical network paths for two websites, and remember, in the real world, websites are not actually hosted identically, is the last mile provider hostile to content from one site versus another? And the things we're trying to do are, first, detect differences in speed, and second, and it's a little bit misstated, detect differences in content. Are things being injected? Someone is out there buying this stuff, because let me tell you, all of us know someone who works for a routing manufacturer, and every routing manufacturer is trying to figure out ways to screw with your traffic. Someone's paying for that screwing. There are repeated news articles about ISPs actually going so far as to replace ads, and companies setting themselves up as ad replacers. This is a problem. This is a threat to the actual commercial success of the internet. We have to do something, and believe me, this is not what I set out to do. I'm going to have to bust out some packet stunts to save online advertising. Are you freaking joking? Bring it on. First off, what's the problem? I call it the Times Square effect. Movies that show Times Square, they digitally replace every single advertisement. Why? Because there's no contractual obligation not to. And certainly, no one who's watching a movie has any expectation that this is anything but a formulated fictional universe. Now, guess what, guys? Carriers are under no contractual obligation to host websites as they say they are. Man-in-the-middle attacks have been something that the web has been built to assume aren't going to happen. The problem is the providers have realized these are really profitable. Wow! I want each of you to think, Google will not sell at the top ranking on their webpage. There is a real demand to be the top link on the webpage. People would pay a lot of money to be the top link, but Google won't sell. You have demand and you have unsatisfied supply. People will modify networks to the point that they can make the money instead of Google. And if it happens to hurt their brand, oh, well, that's Google's brand. Oh, well. It's not theirs. The reality of advertisements is that users tolerate them. They're actually okay. You know, maybe you click on them, maybe you don't, but certainly there's no massive open revolt. And you know what? The people who actually do run ad blockers, you know, believe it or not, those people may not actually be the target market. They're not clicking the ads. The problem is which ads actually do get shown. And there's a huge market to be the one who provides the ads instead. So, the obvious solution everyone says is, oh yes, you know, the entire web should go SSL. Unrealistic security people who don't understand the scope of the problem they're trying to solve and thus make recommendations that have no ability to be implemented in reality, a little problem. This is a hideous solution, but it does respect reality. First off, why can't every website go SSL or TLS? Ignoring the performance issues, which it is true, you can throw enough money at the problem and you'll get high enough performance for SSL. It turns out most websites are done what's called virtual hosting. Meaning, the website you get is dependent on the DNS name you use to retrieve it. So you have lots and lots of names that all go back to one address. It's just like we were talking about earlier with DNS rebinding. Names are different than addresses. You know, it's actually the same in the real world. You have one address that's an apartment complex. Lots of people live there. So it's just the same with the web. Lots of people live at the same hosting providers. But here's our problem. When you do SSL or TLS, you don't get to say, oh, but who I really wanted to speak to was this site, or that site, or Alice, or Bob. You just say, hey, you up there at this IP address, who are you? And only one name can come back. Now, there is a TLS extension to fix this. It is actually supported in Vista. But it's going to take a while for it to be generically supported. It's going to take a while before you can presume every client coming to your website is able to say, hey, can you prove you're Alice? Or, hey, can you prove you're Bob? Right now, all they're saying is, hey, who are you? Oh, you didn't say you're Alice or Bob or Charlie or whatever, so I'm going to reject you. That's what's happening now. The ability of most sites to use SSL is actually massively restricted. All right. So one idea is we're going to use SSL or TLS not as a generic solution for acquiring content. We are going to use it just to get ourselves a loader. We're going to get a Flash applet. We're going to get some JavaScript. We're going to get some Silverlight. And what it's going to do is it is going to insecurely retrieve content for us. Yep. But then it's going to go ahead and use the HTTP session keys, and it's going to use it as an HMAC. Or it's going to find some way of deriving an HMAC. Now, the key that it gets is going to come over the SSL session. It's going to download content insecurely, and it's going to see if this insecure content matches hashes. If it does, great. It goes ahead and it pushes it into the DOM. It turns out I've become a bit of an, it's not actually that hard for a Flash object or Silverlight object or Java object to go ahead and push things in. So what I'm saying is we load one of these apps over SSL, we download stuff insecurely from existing frameworks, we see if it is the valid content according to hashes, and if it is, then we push it down. And that, believe it or not, actually works. I'm building a system to actually do this in a generic way. It's called NDK. It stands for not Domokun. And it should work. A reminder, the reason we have SSL in the first place is because the commercial people were like, we would like credit card numbers. Credit card numbers equal money. We like money. That's why we have crypto in the browser at all. Believe me, it wasn't an automatic thing. A note to a slightly different audience. To people who like sniffing traffic, ad replacement is going to drive the entire web to encryption, because without it, the average website will be unable to pay the bills. The performance issues of SSL pale compared to the damage to sites of being unable to actually make sure the providers host their ads. If you want this not to happen, you might want to get the carriers under control. Now, is it possible, this is where the real fun stuff happens, is it possible to get better data regarding the inevitability of all of this? This is fun. Now we get some old school packet stuff. Who here knows where transparent proxy is? Cool. Transparent proxies go ahead and they take all traffic from your client, wherever IP you're going to, it says, oh, this is port 80. I'm going to redirect it to this box. It is going to aggregate here, inside provider network. This is interesting. Among other things, it means that without even a DNS for binding stunt, Flash can download an applet from, the IP address for Docsparrow.com. Flash can connect to port 80 on Docsparrow.com and can say, please give me Google. Docsparrow.com doesn't have Google. But guess who does? The provider cache. It's right there. Because by the time that connection gets to the transparent proxy, the fact that it was going to the Docsparrow IP has been lost. And it just sort of assumes it was originally going to the Google IP. That's a nice assumption. Now what this means is that, what did I say earlier about our requirements for detecting provider hostility? We needed to filter out all the other networks. Well, guess what? The transparent proxy isn't sitting on the internet on some random location in the middle of the core. That's within your provider network. If the transparent proxy hosts some things at some speeds and some things at other, you have detected network provider hostility. Very, very simple. But what if it's not a transparent proxy? What if it's just a silent sensor? In other words, you still have the existing packet streams. But it goes, oh, I see a host for this, I'm going to speed it up. Or, oh, I see a host for that, I'm going to slow it down. Well, now these arbitrary connections still going to port 80. Now it actually is making it all the way to the Docsparrow.com IP address. But you know what? When I go to Docsparrow.com, I can ask for 10 megs from CNN, from Yahoo, from Fark, from wherever. And if then content, now what we're looking for is we're looking for a silent sensor that is interrogating the stream enough to know what host it's trying to go to. And if the same exact server can host content at different speeds just by impersonating different identities, you have detected provider hostility. Now here's the problem. I am not the only packet jackass out there. In every major networking company, there's some protocol guy just as smart as I am saying, oh yeah, well I'll see that your IP address was wrong. Oh yeah, I'll see your TTL was wrong. Oh yeah, I'll see, okay, fine. I'm going to go ahead and defeat myself here. Is it possible to build a hostility detection system that uses traffic completely and utterly indistinguishable from real-world traffic? Well, let's see here. We want to spoof sites on the internet. We want to know what these sites would see. We want to be able to respond as if we were these sites, and we don't want the real sites to interfere with our interference. You know, good luck. That's not really possible. You need to have, I don't know. Well, you need to have the sequence numbers. TCP uses these random numbers to prevent random people from just injecting traffic. And because HTTP is built on top of TCP, I, as a guy in the middle who would like to go ahead and impersonate all these sites, I don't know these sequence numbers. So I guess there's nothing I can do, right? Oh, browsers are extensible. Holy crap! So I go online, and apparently you can download an ActiveX object that puts a packet sniffer in a browser. It fires JavaScript packets, object, events on packet reception. I don't think I've ever cackled with such evil glee in my entire life. In fact, Packet Clause's Coming to Town was being sung around the office. Oh dear. So I'm creating a tool called Inspector Packet. What normally stops Mallory from pretending to be a random site on the internet? Well, Mallory doesn't know the sequence numbers the client will use, and Mallory is going to have to compete with a real server for the sending of data. Well, what do we have at hand now? What is our secret weapon? We have a sniffer that's going to leak those sequence numbers over to Mallory. So now that Mallory knows the sequence numbers from the sniffer inside of the browser, Mallory can go ahead and send the appropriate stuff to the client. But what are we going to do about the server? You know, the server was talking to the client. Well, if you remember the stuff from the Chinese attack, just send a reset. Hey, server, client's gone. It's not talking to you anymore. You can go ahead, tear down that session. Client is still going to send acknowledgments over to the server, but this is this great moment where the changes in internet security totally act in my favor. Normally, the client would acknowledge all this traffic because Mallory's spoofing all these packets that are correctly in window. Mallory's spoofing all this traffic. Client acknowledges it over to the site, over to CNN, over to Yahoo, wherever. Normally, Yahoo would be like, "What? Why are you talking to me? I don't have a session open to you. Stop it." But we got firewalls now, and the firewall's like, "I have no idea who you are. You must be trying to attack me, so I'm just going to shut up." Guess who is actually going to receive that? Well, you know, Mallory is not in line with CNN, Yahoo, whatever, so Mallory is never going to see that traffic. Except Mallory has a sniffer on the client, on Alice. And the client's actually going to feed Mallory all these acknowledgments over JavaScript. I call it Ajax, TCP acts over Ajax. Tunneling is fun. So, I saw this article on Slashdot. The goal is to identify the application used on the network, but some of these devices can go much further. Those from a company like Neris, for example, can look inside all traffic from specific IP address, pick out HTTP, look at Gmail, assemble mails as they're typed out by the user. Oh, you're going to look at what a server's doing, huh? Who says you're actually talking to the server? Given a colluded client, which of course I'm developing, Given a colluding client, I can impersonate anyone who doesn't act my traffic. I can generate arbitrary traffic. Oh, you think Gmail's saying what now? I can provide deep packet inspectors with a whole new realm of stuff to inspect. So I recommend inspecting this deeply. Very, very, very deeply. Conclusions. DNS rebinding threatens the boundaries of your network. There are multiple rebinding mechanisms. This will not be trivial to fix. Anyone who says it is on crack. The web could use some real work on its underlying security models. Unfortunately, the stuff that we have is very good for public use, not so much for private. I want to really say that Adobe's done a lot of work in this regard. I really respect it. We may need to consider applying at least integrity and perhaps encryption to all web traffic on the internet, because if we don't, advertising is going to die. And there are mechanisms for detecting provider hostility, and if you are trying to deploy them, I'm watching you. So that's what I got.